interesting data structure called the cache. Yes, this is 50 cent, and he has, you see, he has a lot of cache. Yeah, he has a lot of, yeah, also he has a lot of, he has a lot of arguments with people. I actually went to his Instagram, and he's not a very peaceful guy. That's what I have to say, but he has a lot of cache. Is he eating the cache? If he wants to, he can eat the cache. So why do we need the cache? Who can? I'm not sure if I made an animation for this. Let's see if I put the animation or I forgot. So yeah, what is this machine on the left? Anybody know? What is this machine? This indeed is the Apple IIe, and the elite people would call it an Apple IIe because it's like totally elite. This is the Apple IIe. It was introduced in 1983. Very, very well designed and interesting machine, which really got Apple into a lot of schools. I think I learned on an Apple IIe at school. It was introduced in 1983. And what is this friend on the right? Okay, this is a MacBook Pro from 2016, right? It was from 2016. So let's compare the properties of these two machines. So this MacBook Pro has a 3 gigahertz CPU. 3 gigahertz means that every second it executes 3 billion instructions, right? So the cycle time, each instruction takes 1/3 of a nanosecond. So 1/3 of 1 billion of a second. And it has 4 cores. So it actually does an instruction 4 times every 1/3 of a nanosecond. And on the other hand, the animation order is broken. It's too sad. I wanted to build a MacBook, the Mac later. So you know what? Let's just imagine it's developing slowly, and you'll just forget what you're seeing for a few seconds, and next year God willing, I'll fix the animation. Okay. So the Apple IIe had an approximately 1 megahertz clock. Very, very, very interesting what exactly was going on there. I'm not going to go into it, but it executed 1 million instructions per second. So its cycle time was 1 microsecond, 1 millionth per second. And it also had memory. Who knows how much memory did the Apple IIe have? So it had, the Apple IIe had 48K memory, and 16K were for compatibility with the older Apples, and like the 32K were like for extended professional use. So it had 48K, 48K RAM. And this RAM was also lots of hacking going on, but essentially this RAM took 1 microsecond to access. And in fact, it had to access it all the time because of, the engineering challenges of that day. But so the Apple IIe took 1 microsecond to access RAM and 1 microsecond to execute the cycle. So if it was like going over an array in memory, everything was fine. Every access would take 1 microsecond. Everything worked lovely. On the other hand, this MacBook Pro, every nanosecond, which is 1,000 times as fast, it doesn't execute 3 commands. It actually executes 12 commands. So it's essentially it's 12,000 times as fast as this one. And if you add hyperthreading, that gets 24,000 times as fast. But the DRAM hasn't been keeping up. If you look at the DRAM access time, and this is a very fast DDR memory, the DRAM access time is 50 nano. And why is it 50 nano? Because you have to select a row, you have to select a column, you have to activate. I'll try to teach you, as time allows, how DRAM works toward the end of the course. But DRAM access is very, very slow. And what does that mean? If the CPU is trying to access memory, and it needs to access memory. It needs to find out, for example, what is the next instruction it needs to run, or what is the data. It will spend most of its time instead of running, on all of these CPU cores very quickly, it will spend all of its time waiting for the DRAM. And essentially, it will be about 300 times slower than it should be. So our challenge is that getting to the memory is very, very slow. Oh, by the way, one thing is also common between these two machines. They don't have a right mouse button. This machine doesn't have a right mouse button. I'm not sure if it has a mouse even, but no right mouse button. It also doesn't have, doesn't support, doesn't run shooters very well. Okay, so how do we solve this problem? We really, really need access. We really need to feed our cores with data very quickly, and we can't do it. The DRAM is too slow. So what do? So yeah, what to do is faster storage. So the idea is that we take a bunch of really, really fast memory, and we use it for stuff that we really use often. And we try to get interesting data into this small cache. Cache is like a machbo. It's like it's where the squirrel hides its nuts, right? It's like a little hideaway. We put the popular data and instructions there so that the CPU can run very, very quickly and access it very, very quickly. So why is this at all possible? What makes this possible, in theory, is what is called the principle of locality. The principle of locality means that we basically execute the same instructions or the same data most of the time. So you can imagine that I have 16 gigabytes of memory on my computer. But if what I'm doing right now is, for example, multiplying two matrices, I'm going to be running the same, 6 lines of code, which go over the matrices. And I'm going to be reading from these matrices, row, column, row, column, row, column, row, column. So I'm going to be using a small amount of memory for my data and for my code, and I'm going to use it very often. So if I take a little subset of the memory, and how do I find out the subset? That's a nice challenge. And I keep it close to the CPU, and I use very, very fast memory technology, then I can kind of work at the speed of my cores and not at the speed of my RAM. And you can imagine that everybody is doing it right now. You can't actually do anything when you're running. You can't get any efficient performance when you're running off DRAM. So this is the concept of a cache. And caches have what is called a cache hierarchy. So the idea is that this is the CPU. The CPU is sitting here. The CPU wants to get data really, really quickly. And this is the DRAM. The DRAM is really, really slow. What we're going to do, we're going to build a little caches closer and closer to the CPU. Each one of these caches is smaller and therefore faster. Why is smaller faster? Does anybody have a guess? Right, so Ria is correct, and Ligdor is also correct. So it's smaller because everything, the data has to travel less, and yeah, physics is always around us. But as Ria and Dimitri are saying, if I'm trying to figure out how do I actually live in this world of cache, the CPU is trying to get to a piece of memory, and now the CPU has to check: is this piece of memory in the L1 cache? Great, I can run really, really quickly. If it's not, oh, I'm in a little bit of trouble. Let's take a look if it's in the next double cache. Is it there? Great, I can run a little slower. It's not there, let's go to the left double cache. If it's not there, oh, then I'm in real trouble. I have to go to the DRAM. So I have to search these data structures very, very quickly. And without even, I'm not telling you how these searches are implemented, but you can obviously understand that if you have a smaller data structure, you search it more quickly. So I want to give you some data from Generation 6 Intel processor. It's called Skylake. So on average, the CPU has the registers, which are internal to the CPU, has about 1 kilobit. It has 64 kilobit per core of L1 cache. This is the fastest one. Then it has 256 kilobits of L2 cache, which is a little larger, but it's still close to the CPU cores. And all of the cores share a left level cache, and you see it's much larger, 8 megabytes. And if you fail, why is it called file? I don't know. And after you fail a search to the left level cache, then you are forced to go to the DRAM. The DRAM is, for example, 8 gigabytes. And the access latencies, on average, you see the register file you can get immediately. You don't need to fetch it. To get something from the L1 cache, you need 4 cycles. L2, you need 12. Left level cache is 42. And the DRAM, you see it's 150 times slower than getting it from the register file. So the CPU really, really wants to get the data into the L1 cache. Now, a little motivating question for after the break. Let's say the CPU really wants to get, it needs to run a command, and it discovers to its dismay that it can't execute the command. Hard disk drive. So it depends if you need to seek first or SSD. Somebody wants to look it up and put it in the chat. I won't mind. It's of course much slower. DRAM is faster than SSD, no doubt. Now there is this Optane thing, which is supposed to be as fast as DRAM, but I still don't have to teach about it. Okay, so I just want to give you a little thought exercise to motivate you until after the break. Let's assume the CPU wants to execute an instruction and discovers that it has to go to the DRAM. So now the core is stuck for 150 cycles. It can't execute the command. So what is the core going to do in the meantime? So it's a motivating question. You can think about it. Of course, the trivial answer is going to sit and think. But you can think maybe we can do something more creative, and that will be after the break. So I want to give you a very, very brief overview of how the data is arranged in the cache. So my objective is to have a small subset of the data that I'm using often in a data structure which is very, very quick to search. And the data structure which almost all of the CPUs I know of use is what is called a set associative data structure. And this is essentially the data structure in the cache is, thank you. Yeah, thank you. Yeah, we'll get to that. You can think about it as a big box. And in this box, you put what is called lines. Lines are little bits of the DRAM that you discovered that you want to cache, and you put them inside this data structure. So each cache line has indicates where did it come from in DRAM. It's an address. And of course, the data, what is the data which is stored in the cache, and some kind of quality indicator. And this grade is going to help me decide how do I evict stuff from the cache. So what is the idea? Obviously, the cache is always full of something. And I'm trying to get something from the memory. And two things can happen. Either there's a cache hit, which means something good happened. I was successful in finding this data in my cache. And then I want to take this line and say, this line is really good. I like it. Let's keep it. So I give it an increased grade. I give it a little bonus. And the other thing that can happen is that, oh no, I searched the entire cache and I didn't find this address I was looking for. So now I have to go and fetch it from the DRAM. It comes back from the DRAM, and I have to put it in the cache. So the caches are inclusive. I have to put it in the cache. I can't use the DRAM directly. So to put it in the cache is full. What do I have to do? The cache is full. I need to put something from the DRAM. I have to git. I have to throw out an entry. I have to decide which one of the entries is going to get thrown out. And you can imagine I'm going to look at the grades and I'm going to say, this line in the cache, nobody's actually using it. Maybe maybe the program was just running over an array and it's never going to go over it array again. So I can just throw away all this array. I don't need it. So the eviction policy means I need to throw a line out of the cache. Which line do I throw? So this is the eviction policy. And the second thing is as the mapping policy. So the mapping policy, a little complicated, but it's important to understand. My objective is to have a data structure which is very, very quick to search. I want to find if something is in the cache very, very quickly. So if I wanted to compare the entire 64 bits of the address and look at all of the entries in the cache, I could have 8 megabytes. I could have, it's thousands and thousands of entries in the cache. It would take me a lot of time. So the data structure that I use in the cache is what is called a set associative data structure. And the idea is that I divide my big cache into smaller groups called sets. And each address in memory can only go into a single set. Of course, this set isn't big enough to fit all of the memory. There is still competition for stuff inside the set. But this mapping policy helps me find which set do I look at. So now, when I have to find out if something is in the cache, I run this mapping policy very quickly. It's a very, very quick function. I found out which set I need to look at. And in the set, I search again very quickly. The size of a set is called the wayness. It could be 12 entries or 16 entries, not much more than that. So it's very, very quick to search. And this mapping policy, this mapping algorithm is designed so that if you have random addresses in memory or like buffers and stuff like that, they're going to be spread out very nicely over the entire cache. So if you're using the memory in a very non-attackful, non-offensive way, you're going to get a nice spread of your data all over the cache sets. So, but if you're an adversary, it means that you can really, if you know the mapping policy and you're very, very creative, you can force an entry out of the set, out of the cache very quickly. Now, one thing I want to make clear before I continue, let's say we have two processes, right? Two processes which are isolated from each other, and they're running, let's say, in different virtual machines. Can these two processes get memory mapped into the same set on the cache? Yes or no? So I have two processes which are isolated. They can't access each other's memory. Can they go into the same set in the cache? Right? And the answer is, as you said, the answer is yes. These processes, each of them is accessing their own memory, but they still go into the same cache set. But they're isolated from each other. How can that be? Why don't you give each one of them a different set? They're isolated. How do the engineers who decide the CPU answer? No, I'm not blaming Intel. Everybody's doing it. ARM is doing it as well. They answer, listen, buddy, this is microarchitecture. It's not architecture. We write the cache. We give you isolation. You can't read out the victim's memory from the attacker. You're sharing the same set. It's good performance. And you don't know the mapping policy because it's a trade secret. We're not telling you this policy. Right? So it's why does L1 cost? L1 is faster than L2. L1 is, you can just review the slide. L1 is the fastest to access. L2 is a little slower. It's the smallest one and it's the fastest one. And L2 is a little. L1 is more expensive than what? L1 is the cheapest one. L2 is 12 cycles. L1 is 4 cycles. You really want things to get from the L1. Maybe I didn't understand the question. Why does it cost more in terms of memory size? I need to think about your question. Let's continue with the question. I'll think about it. Okay. So